Okay, so we're back here with this is technically from lesson 6.5. Talking about applications of integration functions. And we did some review problems already that are things that you've really already seen, but this example 3 is kind of where we tie everything together. And you've actually already done these types of problems too, but we just have to think about how we're naming things and identifying things, labeling things, stuff like that. Okay, so I've given you a function. This is a graph of f, all right, a function f. But I've defined this other function, this is an integral function, g of x, as being the integral from -3 to x of this function f. Okay, so anytime, if you look down at the question I'm about to ask you, if I'm asking you something about the g function is the integral function. So that's going to be an area of some kind. Okay. What about when I ask you about g prime? Well, this is what we learned yesterday, is that if I take a derivative of an integral function, what I'm really left with is just the f function. That's this thing, okay? And so here's the important relationship to understand. If g is the integral of f, then f is the derivative of g, okay? So I'm going to say that one more time. If g is the integral of f, then f is the derivative of g. So if I'm asking about the derivative of g, I'm really asking about the f function, which is just the graph. Okay. Well, what if I then ask you about the second derivative of g? Well, the second derivative of g is the derivative of the first derivative, which means it would be the derivative of f. Okay. And the derivative of f, if I have f in front of my face and I'm asking you about derivative of things from this graph, that's going to be your slopes. Okay, so I would always start by kind of identifying this information for yourself first when you start one of these problems. Okay, so identify what is it that you're looking at, and then that way when you go to each one of these problems, you can sort of consult this and say, okay, am I finding an area? Am I reading a value off the graph? Etc. The other really big connection I want you to make is I want you to think about all of those problems we've done where I've handed you a graph and said, hey, this is a derivative graph. And we were able to answer all these questions like this. Look at what's coming up. Critical points, inflection points, all of those things are coming back at us again because really this is one of those questions in disguise. This is a question where really what I'm giving you is a derivative graph of this g function. And so you can answer all these things about g using all that information we already knew about derivatives. Okay, so let's just dive into one of these. So these first four, notice, are all just asking about the g function. The g function is the integral function, which means I'm finding areas. So for example, this one wants me to find the area from -3 to 0. So here's my -3, and I want to find the area to 0. So that just looks like a trapezoid to me. So I have this would be the height of my trapezoid down here. This is 3 units. And then I have a height, or I'm sorry, a base of 2 and a base of 1. So this area I am finding by doing 1/2 times 3 times 2 plus 1 for my two bases. That's 3 times 3 is 9 over 2. So this area is going to be 4.5. And so then this answer is just 4.5. Okay, this next one, g of -3. Well, that's asking me to find an area from -3 to -3. We know how to work with that too, right? -3 to -3, that area is just going to be 0. That's standing still in one spot. Okay, how about the area up to 2? So again, we're starting at -3 and going up to +2, which is up here. Okay, so I already know this piece is 4.5. What I need to figure out is what these little spots are. So I think what I'm going to do is find the area of this. I'm going to treat this like a rectangle here. Okay, so this rectangle is 2 by 1. So the blue rectangle here has an area of 2. Just kind of putting that there for safekeeping. And then the area of my circle, this part, has a radius of 1. So it's going to be pi times 1 squared. And then I have to divide that by 2. So that's going to be pi over 2. And all my areas are getting in my way. But so when I look at this area, which is what I actually care about, it's going to be the area of the rectangle, which is 2, minus this value, which is pi over 2. So this area here is 2 minus pi over 2. And so if I want the area going all the way from this -3 up to this +2, I'm going to have 4.5 plus 2 minus pi over 2, which is really 6.5 minus pi over 2. Okay. And then the next one wants me to, again, start at -3. So notice every one of these started at -3 and go all the way up to 4. Well, the good news is I already know all of my area up to 2. So now I just have to think about what happens when I go to 4. Okay, I want you to notice that this little piece is a triangle. And then I have that exact same triangle living right here. Okay, they both have a base and a height of 1, base and a height of 1. This one's positive and this one's negative, and those two little triangles are going to have exactly the same area. So when I add those both together, they're just going to cancel each other out. So it's really like I'm adding a big fat 0 to this answer. So I already had all of my area added up to here. This is going to add, technically that area would be 1/2, but then this is going to subtract 1/2. And so my answer for this is actually going to stay exactly the same. Okay, so all of those were just finding areas. Now these next couple ask me about derivatives. Well, remember the derivative of g is just the graph of f itself. Okay, so now I'm not finding areas anymore. I'm just reading values off the graph. So g prime of 1, maybe I'll do this in a different color so it doesn't blend in with everything. G prime of 1 is asking me what's the value of f at 1. Saying what is f of 1? Well, f of 1 is just 0. Okay. Well, what's g prime of 0? G prime of 0 is the same thing as asking me f of 0. And f of 0 right here is equal to 1. Okay, now let's look at second derivatives. Second derivatives are really what f prime would be. So it's what is the slope of this graph. Okay, so g prime at -1, let's see, do I have another color? Of course I have another color. At -1, that's this point right here. And so what I need to know is what is the slope of that line segment that that point is on. Okay, and I'm probably going to use these endpoints here. So I'm going to do y2 minus y1. So 1 minus 2 over x2 minus x1, 0 minus -3. That's -1 over 3. And that would be that's g double prime of -1. That's the same thing as me asking what is f prime of -1. All right, g double prime of 3. Okay, so let's see, I scribbled all over things here, but that's 2. This is 3. Okay, so I need to know what is the slope at this point right here. And again, really what I need is what's the slope of this segment. So if I use y2 minus y1, I'll have -1 minus 1 over 4 minus 2. That's -2 over 2, which is just going to equal -1. And again, the question I was really asking here is what is f prime of 3? Okay, let's answer some more derivative questions. So when is g of x increasing? Okay, anytime I ask you questions about increasing and decreasing, okay, what I'm really asking you is when is g prime positive, right? When is the derivative positive? Because that's how you know that a function is increasing. Well, let's look up here. G prime is really talking about f, which is the graph. And so anytime this f function is positive, meaning living above the x-axis, g is going to be increasing. So I want us to read that off the graph for a second, and then I want to come back here and talk about this function, and we'll hopefully make that make sense. But I am positive everywhere from here all the way to here. Really everywhere except these two little tails on my graph are positive. So I'm going to say this starts at -4 and goes all the way to +3. So I am increasing on the interval from -4 up to +3. And again, my reasoning for that would be because G prime, which is really f, is greater than 0. Okay. Um, think about this for a second. The g function is the area function. And so when is your area getting bigger? Well, this little segment over here, starting at -5, this is negative area. So that area would not be getting bigger. That would be decreasing because it's negative area. But as soon as I cross this point, all of a sudden I'm adding positive area back on. And I continue adding positive area. My answers here were all getting larger. Well, it started here. So this and then this and then this, they were all getting larger up until this point here. And then I started shrinking again. But all of this is adding positive area, so my area would always be increasing. Okay, let's think about critical points. Okay, critical points of g of x. Well, critical points happen when the derivative is equal to 0. So the question I'm asking myself is, when does g prime equal 0? Again, g prime is really f. Okay, and that's this graph. So when is this function equal to 0? Equal to 0 is when I'm on the x-axis and I see 3 critical points here. I see a critical point at x equals -4. I see a critical point here at x equals 1. And I see a critical point here at x equals 3. This didn't ask me to justify, but I'm trying to put some justifications in here for your notes, because that's when g prime, which is f, is equal to 0. Okay, let's think about inflection points. Okay, inflection points happen when, again, let's think about your derivative. What is your derivative doing at an inflection point? We need g prime to change direction, meaning from increasing to decreasing or vice versa. If I was writing this as a formal, like, free response question, I would be more specific than change direction. I'm doing that just for the sake of us kind of looking at this graph and figuring out what's happening. Okay, well, again, g prime is really f, so I want to look for the places where this function turns around. And so this is increasing, 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 and then all of a sudden here it turns around and goes decreasing again. So this is going to be an inflection point, okay? And then I'm decreasing, decreasing, decreasing. Now there's a sharp turn here, but it continues to decrease. So that's not going to be an inflection point, okay? But right here is where I switch from decreasing back to increasing again. So this is going to be an inflection point. And then I'm increasing, increasing. Oh, and then here I turn around and go back to decreasing. So here is an inflection point as well. So I have an inflection point at x equals -3. I have an inflection point at x equals +1. And I have an inflection point at x equals 2. And again, my reasoning is this right here, because that's when g prime is changing directions. Okay, where do I have a local minimum? Okay, we know this has to happen at one or more of the critical points. Okay, so we want to look for a critical point. So we need g prime to equal 0. And the way we know we have a minimum is our function would be decreasing and then increasing, which means my derivative would be negative and then positive. So I would want g prime to be equal to 0 and changing from negative to positive. That's what I'm looking for. Okay, so let's look at those points that we identified as critical points. My graph is getting awfully messy here, but these are the points I'm looking at right here, my critical points. Okay, at x equals negative 4, okay, this point right here, my derivative is changing from negative to positive, which is exactly what I was looking for, right? So I would say at x equals negative 4, because I have a derivative, and remember this graph is my derivative, that's changing from negative down here to positive up here. Okay, so my original function would be switching from decreasing to increasing, and that's how I have a local minimum. Let's check at x equals 1. Okay, x equals 1. My derivative is positive here, but then it's positive again here. It never dips down into negative territory. Okay, and so I don't actually have a direction change. This would be one of those situations where my function is increasing and then levels out for a second, but then keeps increasing. It would be something like that. Okay, because I have a derivative that's positive here and positive here. So it hits 0 for a quick second, but it never switches direction. It never goes down into negative territory. And then my last critical point was at x equals 3. This point right here is a critical point, but I see my derivative changing from positive over to negative, which is the opposite of what this would be. So this point right here would actually be a local maximum. Okay, well, this point here is a minimum. Okay, so x equals negative 4 because g prime, which is f, changes from, and really I wrote this up above, but I'm just writing it for the sake of having a justification, from negative to positive. So again, I wouldn't say because it changes from decreasing to increasing. First of all, be super careful about using words like it here. In fact, don't use words like it, because what it are you talking about? We have so much going on in these problems. So make sure you're super specific about what function you're talking about. And then remember, you always want to talk about the thing that you're actually seeing. So I'm not seeing this. I'm not seeing a decrease and then an increase. I'm seeing a derivative that's changing from negative to positive. So that's what I want to focus on in my justification. Okay, and then one last question here. Okay, when is g of x concave down? Okay, well, that's going to happen when my second derivative is negative, which is the same thing as saying my first derivative is going to be decreasing. So I am looking for when is g prime decreasing. Okay, and again, g prime is just my f function. Okay, so this is all increasing, 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 increasing. That orange circle right there, that's an inflection point that we circled earlier. So this is a place where the concavity changes. So all of this is concave up. And then everywhere that I'm decreasing, so starting at negative 3, decreasing, 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 and then even after this point, I keep decreasing all the way to this orange circle. All of that is decreasing, which means it has a negative slope, which means my second derivative is negative, which means that my original graph would be concave down. Okay, so I'm going to say the interval from, whoops, and these ones should use parenthesis brackets, negative 3 up to positive 1. Okay, let's see. Oh, I'm sorry, you can't see my stuff there. Have me zoom this out just a little bit. I'm using a not great camera, so when I zoom it out, it gets a little blurry. But so from negative 3 to 1, okay? And then this function turns around and is increasing again, but then we see another orange circle here because once again I change direction, and after this orange circle, I'm back to decreasing. So this again would have a negative slope, which means a negative second derivative, which means concave down, right? So from 2 to 4, That would be another place where I'm concave down. Okay. And my justification would be, again, I want to talk about the function that's in front of my face. Sorry, my camera went away here. Okay. Talk about the function that's in front of your face and what you're seeing. What you're seeing is that G prime, which is F, is decreasing. And you could get into all of that stuff about like, okay, so that means the second derivative is negative, which is why it's concave down, blah, blah, blah. But honestly, this is sufficient. So stick with like what you absolutely have to have written down, because the more you say, the more there's a possibility that you'll make a mistake in something that you say. Okay, that was a lot wrapped into one problem. Um, so, take some time, digest that. I'm going to do one more. Actually, what I'll probably do is just post this, but on this next page, this is just sort of a summary of everything that we talked about. Like when we're looking at an integral function, what are you looking for all of these things? And honestly, this is going to be very similar to that chart that we did earlier this year when we looked at all the derivative graphs. It's just now reframing our thinking around integrals. Okay, so I will just post a printed copy of this instead of talking through it on the video, because it's really just a summary of all the things we just talked about. Hopefully that'll be helpful to you, and don't worry, we'll get plenty of practice with these in class.